Okay.
Stage is yours. Please go ahead.
Quick reset just so you can get the proper time.
Okay. So yeah, thanks for having us here. It's a great honor to speak to you all. I remember listening in last year, and this year I wanted to be somehow in person, so it's so much better. Yeah, I'm Roland Kuhn, founder and CTO of Actyx. This is José Duarte. He's a distributed systems engineer, and yeah, we'll talk about what we implemented at Actyx, roughly, just very briefly, but then more about lessons learned. So people have built applications using the model that we implemented, and some things worked, some didn't. Noteworthy here is we approached the local first angle from a different side than was presented so far. So for us, it was not like, oh, there are CRDTs and we can have data agency and ownership. This is not where we came from. So our background is we need to construct systems that just never stop. And the reason is our customers make software for factories and not for the back office, which is totally fine if you shut it down for an hour or two. No, it's for the coordination between what happens on the shop floor, so between the machines and the material and the persons manufacturing actual things in actual factories. So this is not only production code, it's also for real production. And just for context, because many people don't know it, factories are not operating on high margins. So if you, so typically like 2-3% margin that a factory has for turning raw materials and energy and work into a finished product. So if you stop the factory for 3% of the time because, for example, a DSL line has 97% uptime, then you're now making a loss and you can shut down your factory. So you cannot use IT on a factory shop floor without answering the question, how do we make it so that it never stops? Then the other thing is, we went to factories and wanted to roll out software, and software needs to run on computers. So the obvious question was, where do we put them? So to cut things short, we decided we want to roll something out without involving factory IT. Because they are really picky and really slow and they just get in the way. So just put gateways like Raspberry Pis on the machines, give people tablets and let them use their phones and so on, and then use a Wi-Fi. So we can usually get a Wi-Fi in these places and then tell people to not connect it to anywhere, and they are fine with that. So if we have this, how can we make a system work? Yeah, so we want to roll out into a factory just giving them devices, and they are supposed to do their computations locally because there is no connection to the cloud, because we cannot afford it due to reliability, and we want to have collaboration between them because a factory is inherently a very collaborative organism. Yeah, so the goods, the raw materials move through a certain step of workstations, production steps, and so on, and lots of people doing things locally and then collaborating with other people nearby to move the process further along and eventually finish the product. So this is where we came from. This is the context. Then we stood in the office at some point and tried to figure out how to build this, and we came up with a key idea how we want to do this. So single writer principle is the only thing that we could think of how we can make something that you can always write to. Yeah? If you're the single writer to something, you can always write. That's totally cool. So we call them events because we believe in domain-driven design and so on, not delta state CRDT operations that are opaque. We give semantic meaning to things. So, and we add these events to local logs. A node can write multiple slices if it wants. Then these log slices are replicated between the nodes. So now at a receiving node, I might have 17 slices. Now, how to make sense of this? I need to merge these logs. And for that, we are using a coordination-free, totally deterministic order based on Lampert clocks and cryptographic node IDs. So we have a merge operation that is deterministic. Now we have a resulting single log, and now we need to make sense of that. And this is the question of a programming model. So how do we interpret these merged logs? Now, what we are getting at here is, since we cannot afford to have consensus because that makes us unavailable at times, the best thing that we can aim for is eventual consensus. So once everything is disseminated, all is said and done, everybody should come to the same conclusion about what the result should be. This is the best we can hope for. There's a link down there, archive number about a paper at eCoop this year, where you can read up the full theory. I will just give you a tiny brief overview. So what we do is we let people design protocols by specifying a global type. And this global type is then projected into local types, just as it normally is for session types, session typing systems. And then we have the local agents, and we can check whether they conform to the types that came out of the projections. So we have a proven theory that has some properties like deadlock freedom, eventual consensus, and so on. We have implemented a type checker that you can, in Haskell and Rust. Rust compiling to WASM, so you can use the type checker in TypeScript using this machine check module. And then there is the machine runner library, which uses Actyx. This is an open source product for shipping these logs around. You can use this to write down your state machines, run them, and get your state of what you would normally call documents. I call them workflows. Yeah, so because in the end, what we're doing here is not just everybody can add text to a document and all edits are accepted in a factory. The point is sometimes also coordination. Only one should do something. And yeah, I can get into the details because I want to talk a bit more about this slide. So you're not supposed to read this slide. This is mostly a reminder for myself so that I can touch upon the points, and you can let it sink in and ask questions later if you have more points that you can think of. So when we asked our partners or customers about their experiences using this system, these were their answers. Consolidated set of their answers. The first one is people are still very much used to talking to a central database, which gives them this godlike overview where I can see everything, I can make the rules, I know that the rules will be followed because I believe that Oracle is correct, for example. But they don't have that here. So they need to think about how would people solve it if they are not omniscient. So people who actually need to talk to each other to figure out what the other person has done. It's possible, if you stay in this metaphor, people get it, but it takes a bit. It's a shift of mindset. Once it's done, they really like it. So the second one is similar. This machine runner presents a very restrictive interface. You use it in TypeScript, but you need to write down your state machine explicitly as a state machine. There is another approach that we might want to try, which is done by another company in a different context called Temporal. They use async await for basically a very similar purpose. So it should be possible to use other language features to make the presentation different. But still, it's rather restrictive, and the reason is that we want to know exactly the shape of the communication so that we can check whether it's correct. Now that's the end goal of it. So at first it feels restrictive, but it makes sense later because in the third line, so what we focused on is this graphical representation. I showed you these state machine graphs for a reason, because people in factories think like that. When you ask them to explain the process to you, they will start drawing on a whiteboard, and it looks something like that. So they can immediately compare the programming diagrams with their own diagrams and then see whether they match. And sometimes you make this protocol design, you make the projection, you implement the machines, and then the programmer says, hey, this doesn't work. There's an event missing here because otherwise it wouldn't do what we want. It doesn't have the right data. And then this loop runs and runs again and finds design bugs in the production processes of a factory. So we've actually seen that, which is pretty cool. Then, of course, you can do this machine check automatically, and that is very nice for productivity. But there are some challenges. So you can always get updates from the network. And if you have asynchronous processes running in your application and you have asynchronously incoming events from the network, you might get into situations where you don't really know which update is the one that you want to deal with right now. So you start an async process and it gets invalidated, for example, because something changed. Also, there is a problem not so much for the programmer, but for the users of this system. So they get this tablet, and if it's not connected to anything, they make changes, and then they ask themselves, why does the dashboard not update? So you need to figure out the UX to make this work. Yeah, I'm stealing too much time, so let's discuss the last ones offline.
Okay. So for my part of the presentation will be, in contrast to Roland's proven theory, this is pretty much vaporware. Yeah, and I'm looking for feedback, ideas, etc. So as for software evolution, we have like two fields. On the data end, we can use Cambria to translate data between different versions of schemas, etc. But on the behavior end, we don't really have that. And in Actyx case, we cannot ensure that each participant has the same version. We have a swarm system, and if one participant does not like to cooperate as a totally different version, the whole system cannot, it's not progress, but the cooperation part falls apart. So yeah, and since Actyx peers are now state machines, the whole question I pose is, so how can we make them cooperate despite their differences? So as I said, on the data end, for example, we change the state names, etc. We can use Cambria. But on the behavior end, so if we want to add a state, as we have here, the 0.5, we need to add new labels, new edges, I mean, and make everything work. So here, my proposal is we do versions instead, because if we just have one label, we will be having not a deterministic machine, but a non-deterministic one. And so the labels with the version stops those conflicts. So let's run through a trace. So we start both versions, V1 and V2. I forgot to tell you, V2 and so on, like all know the previous versions of the state machine. So the state machine doesn't get edges taken off. So we start at state 0, we do turn on V2. Machine 1 does not progress, machine 2 progresses. So we do that again, and we now have an inconsistency because the old machine is still at 0, the new machine is in 1, and they both know the same, they both know that state, so we have an inconsistent state for the system. If we instead replace the V1 in the last edge with V2, the V2 with V1 in the last edge, we now get the same transition in the middle, but when we do the last one, they both converge to the same state. So yeah, this is a really brief demo. And as for the next steps, we still need to figure out a bunch of rules, formalize everything, build a proof of concept, and profit, I guess. So yeah, we are now open for questions.
Thank you.
Hi, this is very interesting. Yesterday at the live workshop, we had a paper about the schema change problem, and we posed exactly this problem as one of the examples, and you have an approach to solving it. So I suggest that you get in touch with us and submit your solution. Thank you.
Yeah, we shall do that. Thanks.
I'm very excited about your talk because it sounds like the strategy you're using is almost exactly the same strategy that I use for Muse for the application I'm working on, in terms of each device has its own logs. It can eventually get those stuff from everybody else, and everybody gets eventual consistency, but can happily operate on its own. I'm curious, in terms of the schema change problem, if you have run into schema changes that are not backwards compatible, whereas in that case you were adding a state 0.5 where V2's start state and end state both had a valid state in V1 as well. Have you ever come across a state that you were not able to represent in a previous version that was entirely new. So it completely diverged as opposed to came back
yeah,
together.
Sure. So as far as we encountered or not, the simple answer is no, because this is still like idea and vaporware. But I'm available to discuss a more detailed approach, because this I also have like a paper, if you want to call it, of sorts, with all the ideas I have. But yeah, like I couldn't put everything here in a 5-minute demo. So yeah.
There's one anecdote I can relate to this. That was long before he joined. We were building software for a factory. They were tracking the work that was being done to gain transparency and then use that to optimize the processes. And there was a change in the sub-process. So the big sequence of production steps was the same, but how an individual starts and stops working, there was a change. Something about the break being handled differently. And there, we didn't have this work yet. We did all of it manually, and it was not possible. So we had to version the whole thing and switch it all at once, because we were not able to figure out how to make it run side by side. So I guess there are such cases where it just doesn't work.
That's been my experience too. I just went through a terrible change the world. That's been my experience too. Most of the time, we've been able to find ways where the two versions coexist gracefully, but not all of the time. And just recently had to kind of stop the world, make sure everyone migrates into the new world, and that's it.
Can you be specific?
So it was actually in the Muse case, it was for authorization, where in the original synchronization, it was only a single user. And so it might be multiple devices for that single user in a local first, but it was a single person. Whereas in the new world, a second user or a third user on the team might come in, have permission to make edits, and then be removed, and their previous edits need to remain, but future edits need to not remain. And so that was the problem for us in terms of needing that schema change, where version 1 did not have that ability to put up a wall and block a client. But we needed to put up a wall to block a client and be able to communicate when that wall should or should not be blocked in time.
Could you pass the microphone?
So the thing that's different than the Cambria model, and this is something that didn't come up in Jonathan's schema change here, so I think I'm going to try and generalize what you're saying, which is that the treatment of the data structurally was determined by the values in the data, whereas in normal schema migrations, you like rename a column, everything that went in the one column goes in the other column. But here, this is a form of migration where how you treat the data depends on the contents of the data, not the location or the structure.
Yes, because we ended up adding data about adding data. Yes, because we ended up kind of adding data about authorization, and that authorization affects how you look at other data. Essentially, is the way that it operates. It's a generalization, but yes.
Okay, yeah, really exciting stuff. I'm also very interested in verifying local first software, and one thing I've been thinking about a lot is also like, could you verify different versions of the same software against each other and reason about their interactions, which is pretty much what you're suggesting here. So I think that's a really cool idea. And I mean, coming from these behavioral graphs, you have a lot of information there, right? You basically know how each version would act in which case, so you can reason about their interactions, which is, yeah, pretty much what you're suggesting, I guess. Yeah, so not so much of a question, more of a comment. Really, really cool work. I'd love to discuss the details offline later.
Thank you very much.
There's one link here. So the theoretical model has this notion of subscription. So not everybody sees all the events. We haven't done that yet, but your question triggered an interesting thought that we might use this feature to try to verify this, because we have already well-formedness conditions for that interaction, so we could see whether they translate into well-formedness conditions on the evolution. That's yeah, thanks.
I have a slightly related question, which is, so you said basically everything on like the ground level, you do everything's eventually consistent, or eventually consensus, as you called it.
Yeah.
But then you also said you do coordination sometimes, where things have to coordinate. Could you talk a little bit about that? Because I find it a super interesting topic.
Yeah, okay, so I think we have 5 minutes. The example here that fits well into factories is the logistics one. So let's say a machine wants some new material, and you have logistics fleets of 10 robots. And you don't want to have a central point for coordinating the logistics fleet. So these 10 AGVs, so these ground vehicles with an arm and a tray and whatever, so they drive around the factory. Now, this has been actually implemented by a partner of ours and is being rolled out in a factory, that they all see the request from the machine as an event, and then they place bids by emitting other events. Everybody sees the other events, and so on. This is not a Byzantine system, right? So every node belongs to the factory. We are not considering malicious actors. So all run the same optimization process and come to the conclusion like node 5 should do it. Then emit an event, and then node 5 does it. Now, what happens during a partition? Because we are not using consensus, so it could be that node 7 is separated, got the bids, but not all of them, and didn't get the decision, makes up its own decision, says, oh, it's me. So node 5 and 7 both start driving, and once they reach the storage, they will come close to each other and hopefully will be able to sync their logs. And then node 7 should see, okay, it wasn't actually me. I need to run a compensating action to abort this mission. This is how a factory prefers it, because they prefer that 2 start driving instead of 0 starting driving.
So you don't really do consensus first, you kind of do then compensation.
Yes, it's a compensation model, yes.
Okay.
What's the Helland paper? Promises, apologies.
Yes.
Does anyone remember the title?
Yeah.
But the idea is like at scale, ultimately, you can't really always coordinate. So at some point, you're just going to have to do your best, and then you end up reconciling later.
Yeah, that was a very influential paper, what concerns me at least.
I was talking to your colleague, and he said that another problem was random electromagnetic interference that disables any wireless internet. Is it your case as well?
So we have one case, for example, where this was also an early customer. They are using the system inside a warehouse with lots of steel drums having lots of different materials inside, and coverage is very spotty. So here, the normal local first CIDT-based approach would also work, but I mean, this is clearly the system that we need to deal with this. So we have sporadic connectivity and sporadic synchronization, and it just works. In factories, this is an actual problem. In my home, it's only a problem in one room, and I have yet to figure out why.
One more question, which is a bit about the programming side, right? Because I see you sell software to companies, so maybe you don't want that to be easy to program.
No, we do.
You do, for you. But are there kind of like for you? Or let me put it like this: what open problems do you still see? Like, what are the challenges you face? I mean, José, you talked a little bit about things you're working on, but maybe you can elaborate on that a little bit.
Yeah. So there were 3 more that I didn't talk about because time was up. Just forgetting compensating actions is one of them, for example, or forgetting to emit an event. And I mean, our theory is deadlock free, but if you program it wrong, then yeah, you get deadlocks.
So in the sense that you have a couple of assumptions that that programmers should be reminded of, like things that they need to do for the system to work correctly. It's good insight.
I was wondering if you had size constraints on the logs that are passed between devices, and so if a device is offline for long enough, can it run out of space to write its own log? And is that a problem you're concerned with, or how have you solved that?
Yeah, that's a pertinent question that we have not yet answered in the way I would like. So currently our devices all have at least 20 gigabytes of memory. That's enough for, so it's like a machine doesn't do 1,000 things per second. We're not dealing with those events. We're dealing with human scale events. And 1 gigabyte gets you a lot of clicks covered. Also with some tricks, they compress really well. So currently we can solve it by replicating everything everywhere. But if you wanted to roll this out to other use cases, you really need selective replication. And that's the next step, obviously.
Do we have any final questions? Otherwise, we can already ask the next speakers to set up. And in the meantime,
No next speaker?
no next speaker. Thank you very much for the great talk.